Hopefully this is gonna work. Welcome to Advanced Audio Hacking Part 4 with the Teensy. I am, as always, really excited to work on this workshop because it's sent to us by the team at Teensy, including Paul, whom I have much to thank for. He's going to be at Maker Faire, so if you're enjoying these audio hacking workshops, then come visit him in the Bay Area Maker Faire in May, and we're going to be there too. It's going to be really exciting. We'll have fun. He'll have some cool new audio hacks for you. But what we're working with, anyway, if you're not familiar, is the Teensy. It is a small microcontroller, and it is optimized for audio. It doesn't have any Wi-Fi, Bluetooth, or other connectivity, but is really awesome for reasons you'll see in a moment. Let me show you what we've got here. So we have a USB cable, micro USB, to plug in the Teensy. I've got some jumper wires and an SD card adapter for the micro SD card. And then we have the whole little Teensy assembly itself, which is plugged into a breadboard. It's got the Teensy underneath here, the audio shield that plugs into it. It's got a microphone, audio jack, volume knob, micro SD card, some buttons and potentiometers, and that's really exciting. You can use them for cross-fading between different audio samples and triggering those with the buttons. And I'm just going to go really fast since we've already been through this in other versions, but I'm new to Twitch, so it's really exciting. And then this is a little video screen that hopefully we're going to end up using today. It's an LCD. Presumably we're going to end up displaying some audio information on it because what it is, today we are going to be looking at different ways of analyzing the sound waves that you're working with and displaying those. So in the last few workshops we covered triggering samples that are stored on the SD card, triggering samples that are stored in the flash memory on the Teensy itself, because the Arduino IDE that you use to program this when you install Teensy Arduino, which lets you program the Teensy specifically, it adds a few libraries, including there's a tool that you can use to convert audio files in wave files into basically code that the Teensy can interpret as sound and playback, and it's really exciting. We've also been using the online graphical editor that lets you set up different ways of interacting with the sound that passes through the Teensy. So let's have a look at what we're doing this time. We've been looking at oscillators and the envelope and mixers, and feedback and delay. Let's see where we're going to start today. Audio analysis. So we're in section 3 of this workshop. If you look up the Advanced Microcontroller Audio Workshop for Teensy, you can find the PDF there. And let me look up the actual address of that for you. I'll find it for you after the stream, I think. So peak detection 3-1, we're gonna probably end up with some Arduino sketches that we're putting together with this. So for some projects, like sound reactive costumes and DJ stage lights, your Arduino sketch needs information about the sound rather than just allowing the audio system to process it. The analysis objects fill this role. So what we're gonna do is go to the PJRC website, which is where a lot of Teensy stuff is kept, including the store where you can buy this audio shield and the Teensy itself, and also you can find all the stuff that you need to download to work with it. So let's see if I can do this without making everything look weird. Okay, so pjrc.com, and we've already got this stored in our history. So pjrc.com/teensy/GUI. GUI, Graphical User Interface. It's what we're using to build bits of code that we're going to put into the Arduino IDE. So what are we working with here? Let's start with peak, the simplest analysis object. So I'm going to construct this sketch as it appears in my little PDF. It's not a PDF anymore, it's a printed document format. So anyway, we've got this, which allows us to interface with the audio shield. And now we're going to add in play SD wave 1. So we're going to play in a wave file off the SD card. We need a couple of peak objects. Let's see. It's not a filter, it's an analysis thing. There we go. Cool. 1 and 2. And then we need I2S1, which allows us to output. Let's see. Here we go. So we're going to output both channels here, but at the same time we're going to analyze both of these independently. Cool. Oh, I'm missing a little connection wire here. There we go. Okay. So the audio PlaySD Wave 1 is sent to both the audio shield and the Peak 1 and Peak 2 objects. A subtle issue is the need for the I2S1 object. All audio systems require at least one physical input or output due to a technical requirement of the Teensy audio library. So you can't just analyze it, you have to output it somewhere. That's really interesting. So now we're going to export this code, copy it, and go into the Arduino IDE. And now we need to go find our tutorial code for this. Let's see, audio library, tutorial, part 301, peak detection. So as with the other examples used in this workshop, this was installed when I installed the Teensy Arduino add-on for Arduino, which you can find on pjrc.com, and I'm going to be replacing this little section here with what I just got out of the GUI. So now I'm going to verify the sketch and upload it to Teensy, which means that I need to actually plug in my Teensy. Let's do that real quick. Oh. My janky ass power cable's getting in the way. But let's see. We have a light on in the Teensy, so that's good. So now I'm going to verify this and upload it. And let me double check that I've actually got the Teensy selected up here. Cool! So I'm using a TT 3.2, USB type is serial. Again, since this takes a little while to compile, go through this again, the Teensy can work as an external keyboard, mouse, or joystick, or a MIDI device. All of this like natively. And I have a pretty fun tutorial for making it into a keyboard. But you can look that up on Hackster.io. And then, yeah. Interestingly, I don't see it in this set of ports. So it'll probably throw me an error, in which case, when that happens, I will deal with it. What I might do is unplug my power cable. Risky business. Because it's getting in the way. Compiling sketch. Error compiling. Oh! Exit status 1. Okay. When I got this before, Paul helpfully jumped on and said that it probably meant that I had too many programs running. And indeed, my computer is starting to run its fans a little bit. However, I did close down a bunch of stuff beforehand, so maybe it's just Twitch disliking me. Or the open broadcasting system that I'm using. So here's pjrc.com. Let's close that. Close the Teensy projects page. But again, Hackster.io. All this sweet stuff that you can build with the Teensy. But in the service of actually building something now, let's close it down. Come on, we can do it! Try again. Cross your fingers for me. Sketch uses 35,600 bytes, 13% of program storage space. Teensy did not respond to a USB-based request to automatically reboot. Please press the program mode button on your Teensy. Okay. Eat. I'm not sure whether I need to re-upload after that, but let's try. Oh, the light has gone off. So the deal with this workshop is that I have never run it before. I've been doing parts 1, 2, and 3. However, each part is done completely from scratch without doing it before. It's very odd to me that this is not responding, but I think it might have to do with the USB issue. If I waggle this, does it help? No. And if I like that, then we get a light again. Okay. Push the button. Light goes off. Reboot. Okay. Cool. Yay. Excellent. So what happens now? I should be able to open the serial monitor and see some weird stuff happening. Oh my god, look at that! That's so cool. Hello. Wait, Weirdly, it's showing... Okay, so what I assumed was happening here was that it was taking a WAV file of... No! It's taking a WAV file from the SD card. Of course it's not taking data from the microphone. No matter what I do... Okay, let's mess around with this, okay? Let's take... This is why I'm never getting through this workshop, is because there's always stuff to play with. So what if instead of saying... play SD Wave 1. How do we... I've already forgotten how we use the microphone in. But let's have a look at our guide here. Okay, we did this a couple of times back. Is it I2S? I think it is. Using the microphone, yeah. Cool. We're gonna do it. Okay, so I2S in. I'm gonna just duplicate. Okay, fine. I'll delete this one first. Choom. I can pretty well remember where everything went. Hey, you. So what I'm doing now is just trying to make it so that we're visualizing the peak audio from my voice instead of from the WAV file. Okay, go away. Whoa. I guess I don't need to duplicate these bits. Doop. Okay, let's try it. I'm really excited. Okay, so what are we going to be doing next? Peak detection, fantastic. So the peak objects give numbers between 0 to 1.0, representing the largest amplitude peak of the audio signal during the time elapsed since the previous reading. So each time it reads, oh, oops. Anyway, each time it reads, it's been keeping track of what's the loudest sound that it's heard, and then when it prints a line again, it's based on what the loudest sound that it heard since the last time it printed a line. Okay, so, well, I should have probably looked through this first, because it makes total sense that it's looking for data from the WAV files and not from the microphone. But what if, audio memory, SPI, mostly SCK, that's the system clock, yeah. So basically this is just playing. I can comment out all of this. Because it's basically saying if the SD card WAV file is not playing, then start playing. And I don't need that. Okay, But it is supposed to wait 10 milliseconds to parse the wave info each time. So it's probably 10 milliseconds between each line of that feedback in the serial monitor. So I'm a little wary of messing with that. This is probably not going to work, but let's try it. Upload. If this doesn't work, we're just gonna move on, okay? But it's the hacker spirit, right? You've always got to try new stuff. Exit status 1. I expected unqualified ID before if. I don't know what that means. Expected unqualified ID. Well, okay. Actually, it's kind of surprising to me that this doesn't have a name of a function before it. Like, this is outside of the usual Arduino loop part. Okay, you know what we're gonna do? We're gonna move on to the next bit, and I'm gonna maybe pester Paul about what this means, because I really want this to happen. But it'll happen soon enough. Okay, so anyway, we were analyzing the audio from a WAV file before we started up with all this nonsense. In fact, I can probably make us hear the audio that was coming out too. So let's go back to where we were a minute ago. We were using SD to WAV. SD WAV. Normally when I'm running like in-person workshops, I'm a lot more focused, but this is playtime. So I've basically undone all the changes that I made to this. We're re-uploading it like normal people, and then I'm gonna plug it into my audio system that I have here at my house. And hopefully we'll be able to hear the audio at the same time that we see it being visualized in the serial monitor. Okay, done uploading. Alright! There we go. Cool. Do we have any more controls in here? I don't see any button or potentiometer controls, so okay. Cool. Excellent. Kill the DJ, cut the music. Let's move on. Looking at the code, you can see the peak objects have functions very similar to other Arduino libraries. The available function, let's find that. Here we go. The available function tells you when you can read more data, and the read functions give you the data. The read functions give you floating point numbers rather than data bytes. So instead of like being binary stuff, it's decimal point numbers. Let's get the music up again. Okay. It's a little distracting. These familiar-looking functions do have subtle but important differences from Arduino's normal usage. With incoming serial data, available and read acts as a queue, where available tells you how many items are currently in the queue, and read removes one item from the queue for you. They are designed to prevent data loss. You want to read the oldest data first, even if it actually arrived some time ago. Audio analysis objects are designed to provide only recent information. The available returns only true or false. When the new information is available, only the most recent data can be read. Audio analysis is designed to lose old information. Some analysis, like peak, gives you the cumulative effect since your last read. That's what we were talking about. So you read it, and then like the next time that you print something, you're saying, what's the loudest that it's been since I last printed a line? Information about smaller peaks is automatically lost as larger peaks occur. Other types of analysis give you information from a recent window in time, where results from previous windows are automatically discarded. Details are on each object's documentation in the design tool. So remember, in the Teensy GUI, you've got documentation for each of these things that you're using on the right side, and it's really well written. This example has code to lower the printing speed. It uses an elapsed millis variable, which is a convenient Teensy feature. Elapsed millis are integers which automatically increment 1,000 times per second. Let's see. Elapsed millis, where are you? I think that might have been the, no, that's delay 10. 10 milliseconds. Oh, here we are. Cool. So this example only prints if msex has incremented past 40. Msex. There we are. So as long as you're... Never mind. Try reducing this number. If you use 0, it will print every time new peak analysis is available. Though very fast, this speed is 1 update for every 128 audio samples, or about 344 hertz. That's beats per second. So part 3-2, Fourier transform. You're probably familiar with this if you have made any kind of thing that like does audio visualization with like red and yellow and green, bars and like low and high frequencies and stuff. So we're getting a detailed analysis of the audio spectrum. The acronym FFT means fast Fourier transform, which refers to a mathematical optimization. FFTs have 2 types of output. Complex output gives you 2 numbers per frequency, and is generally needed if you will turn the frequency data back into an audio signal. The Teensy audio library provides the simpler real output, where you get a single number per frequency. The numbers tell you the amount of signal found at each frequency without any information about its phase shift. So we're going to draw a simple system, it says. Fantastic. We're getting an SD wave file in, something from memory here, and a waveform. Cool. Even with the FFT optimization, a 1024 point analysis, which provides detailed results, will tax Teensy's computational power. So only a single FFT 1024 object is used. So everything is getting mixed to mono. The stereo wave file is mixed to mono for the sake of analysis. Cool. So let's build this. We need to play SD wave, play mem. Let's have a look at this. Play a short sound clip stored directly in memory. So yeah, that's this is that weird stuff. We'll have a look at this in a second because it's really interesting. Waveform 1. Okay, let's go grab a waveform. There we go, and a mixer. Where's our mixer? Here we go. And an I2S output. Know that there's 2 of these. There's I2SS and I2S, and then we have an FFT output. It's probably under analyze. Yeah, there we go. 1024. Cool. And then of course we have this guy which connects us to the audio shield. So now this is a little complex. Let's see. These guys go here. You go here. You go here. Then we have outputting to both channels of I2S1 and the FFT. Cool. Now export. Oh, this is so cool. We're getting so much cool graphical stuff here. And we want to paste this into the next tutorial. Audio tutorial and Fourier transform. Fourier transform. I'm not actually sure. I don't speak much French. Oh yeah, if you want to save your changes, then you've got to save it as another file. Let's see. So now, like we saw before, you're playing a short sound clip stored directly in memory, and basically it takes your wave file and turns it into, oh no, broken link. Anyway, it turns it into one of these files, which is just like, it allows the Teensy to reproduce this sound just from like these little hex number things. I think it's hex. 0x? It might be. I mean, it's got numbers in it and letters, so that must be hex. Okay. Anyway, stores it as a hex file, C++ file, which is nuts. Like, that's audio right there. You can listen to that. And we're going to, in like 2 seconds. Verify the sketch and upload it to Teensy. Let's do it. When you run the code, this should appear in the Arduino shield. What does that even mean? What is this? Oh, it's gonna be a time series of numbers for each. Oh, cool. For each frequency. So you're actually getting individual values for each frequency band. That's really cool. Let's have a look. It's still compiling. The FFT analysis produces a tremendous amount of data. This rapidly scrolling window shows only the first 30 of the 512 frequency bins. So I guess low frequencies? However, these 30 are much more important than the remaining 482. Okay, never mind. Let's look. Later we'll look at why that is. For now, let's concentrate on understanding these numbers. We got an error! Exit status 1. Too much stuff running? I quit everything I could. Paul, don't do this to me. Don't save. What can I close? Sorry, you're gonna get a little bit of meta here. Okay. Well, let's see if it'll work now. I'm actually on Twitch now because Google Hangouts on air has been a jerk this morning. It's a little unnerving because I can't actually see what I'm showing to the camera. So when I'm doing this, I hope that you can actually see, you know, the teensy and stuff because it's really cool. But oh no, error status, exit status 1. Oh, we can't handle it. I'm giving her all she's got. Each frequency bin represents the amount of signal found at a particular frequency. The bins are 43 Hz apart. Oh, cool. Oh, thank goodness. Okay, cool. So 43 Hz apart, that means that at, for example, you know, if you have one at 200 Hz, which is right down at the very baseline of human hearing, 200 beats per second is like a really low noise, and our peak is about, I believe, 20 kilohertz, which is like, you know, 20,000 beats per second, a really high-pitched noise. And these are about 43 Hertz apart. So that's a lot of samples. What does it start at? It starts at 0 Hertz. Okay. So actually the first, you know, few of these I wouldn't be able to hear, but we can see because of Teensy. Cool. Cool. So when she's singing up high, you're gonna see like more of these high up numbers in the treble range. And then when there's more bass, you're gonna see more in the low ones down there. Cool. Feels like being in the Matrix. I just see soprano, alto, whatever, blonde, brunette. Guitar listening test. Ooh. If you press the 3 buttons, you'll hear each activates one of the 3 signal sources you drew in the design tool. Aha! So that's how we've... Okay. So we've got the SD wave file, and then we've got this memory stored file, right? But we were hearing the one from the SD card. Ooh, it stopped. Oh, okay, yeah. And then if I push these buttons, I can switch. This is this hexadecimal file. Isn't that nuts? And even just that, like, that's really short, right? And that is all these numbers. Isn't that rad? And then the third one we've got, interesting. Okay, and then the third one we've got is like a synthesized waveform. Now let's open up the serial monitor and have a look at that. Whoa, cool. Wow, awesome. And then here's our guitar file. Cool. You can totally see him or her bending the note there when it wiggles back and forth, right? Oh, whoops. There we go. Awesome. Well, this is rad. Let's see what next. After the sound stops, it's easy to scroll up and see the notes. In this screenshot, you can see the moment that the string is plucked, which results in a few lines with rapidly changing numbers and many frequency bins. Because of harmonics! So even though the person is only plugging one string at a time and playing one note, technically, because of a guitar has, harmonic frequencies that will be played on the same string, it's got, like, multiple frequency bands. Music theory! Yeah, cool. What's next? We have no patience. We must be going. Let's see. Experiment with thresholds for data visualization. Visually detecting patterns in FFT data of composed music is much harder than a single instrument. Probably because everything's all smashed in there together. So when we got, like, a guitar, you can easily see that there's mostly one note, even if you've got those harmonics in there every once in a while. But when you've got, like, 4 different instruments going on, who knows? The many separate sounds often overlap in frequency bins. Human hearing and the brain's ability to discern complex combinations of sounds is pretty amazing. To improve things a bit, find the print number function near the end of the example. Ooh. Let's see. Print number. Ooh, this is not the same thing. Near the end. Here we go. Oh, the function, right. This is where we're defining that function that we use up there. So, we're going to define our own threshold here. Editing the threshold, increase it from 0.004 to 0.024. This will print less detail, allowing you to more easily see the numbers for only the stronger sounds. Cool. That's probably a decibel level then. Cool. I wonder what our range is here. Maybe 0 to 1? Let's find out. The first song that automatically plays is Where Are You Now, featuring Wolfsky singing. She has a strong voice, which usually shows up as 1 or 2 columns of numbers scrolling by, as in this screenshot. I made a screenshot here. Again, you can find this PDF online. Cool. Please don't fear me, because I know what I want. Please deliver me that song. So her voice is over here. Makes you freeze time, staring in at yourself. It's time to step outside onto the path you once made. That was a guitar there. I wish I could point at my screen and y'all could see it. I guess I can just use the cursor. Unlike the acoustic guitar piece for the middle button, the guitars and other instruments in this music have many complex effects applied. I'm going to switch it to something simpler for a minute. Those effects which produce rich and complex sounds tend to scatter the instrument's numbers across many frequency bins. Because the bins add up to the signal's total, the numbers in most bins are lower, mostly below this higher 0.024 threshold. If you have extra time, which we don't, let's just skip that. Try adjusting the threshold to see if other types of sounds become noticeable in the scrolling data. I'm not going to do that because we need to move along, but you should totally get the materials for this workshop, build this little guy, and try it for yourself. Again, step 7, optional. Understand Fourier transform mathematical limitations. The right button plays pure sine waves. Each time you press it, you'll hear a higher pitch until it cycles through all 12 musical notes. The exact 12 frequencies it plays are from this array. If you previously restore the threshold to 0.004, we're not going to do that right now, but maybe after. Oh, there's so much stuff here. It's really exciting. Check out all this extra diagrams and stuff. This is a lot of bonus material. But you know what? We're almost done here. Let's do it. Okay, so I'm gonna edit the threshold, as he says, back down to 0.04004. Upload this. By default, the FFT1024 object uses a Hanning window, which causes frequencies not exactly on an FFT bin to cluster in the close by bins. So we should see like a strong central number and then like smaller numbers outside it. But it also smears the data across several nearby bins. So yeah, we've definitely got some smearing. We've got 0.3 and 0.4 here in the middle. Then we've got, 0.0 whatever over to the side. This shows a limitation of the Fourier transform. Ideally, you'd like your 220 Hz frequency to mostly appear in the 215 Hz bin, with some perhaps in the 258 Hz bin. The Hanning window gets you close, with 0.496 in the 215 Hz bin and 0.290 in the 258 Hz bin. Well, obviously that's going to be different because I've been mashing this button too much. Oh yeah, here we go. 0.496 and 0.90. Close enough. But 0.211 ends up in the 172 Hz bin, and small amounts go to the 129 and 301 Hz bins, which isn't so desirable. They all still add up to 1.0, the original signal size, but they're smeared across 5 bins. We see the same effect. You can disable the Hanning window by editing this code. Just uncomment the line, this bit, which sets the window to null. Where's this? I wish we had line numbers in the PDF here. Mixer 1, again. This guy? But that was 300. Confusing. Oh, I see. It might be this one. FFT1024_1.window function null. Let's just look for that. FFT. Aha! Cool. So uncomment the line which sets the window to null. Your signal will be processed by the FFT without any window processing, i.e. Hanning window, not serial monitor window. When you press the button for 220 Hz sine wave tone, you should see this with the window disabled. Ugh! That means that we've got values all over the place. At first glance, this looks pretty horrible. But if you read the actual numbers, you'll see the 215 Hz bin has numbers between 0.971 to 0.992. Now, I'm not sure which bin is which here, because they're not labeled, but I do see some clustering around here, like 0.903, that's pretty good, 0.905, and that's definitely much better than we were getting before, which was, sub 0.5. So let's see, so almost all of our 220 Hz sine wave did go into the 2 desired bins. However, some of it got scattered across almost all the other bins. This problem is called spectral leakage. I'm sorry about your spectral leakage problem. The windows are meant to prevent spectral leakage, containing all the results to only nearby frequency bins. To understand how a pure 220 Hz sine wave becomes data in all those frequency bins, consider this plot of 4096 points of a 220 Hz sine wave, sampled at 44.1 kHz, which is a pretty common audio sampling frequency. The green box is 1024 points, where the FFT analyzes the spectrum. The FFT reports the spectrum based on the assumption that the waveform is periodic, that it repeats indefinitely. Here is the same 220 Hz waveform, with the first 1024 point section repeated 4 times. Without a window, the FFT is returning the spectrum of this waveform, which differs from the intended 220 Hz pure sine wave. Without a window. The window function is just another waveform, which the signal is multiplied by before the FFT. The Hanning window is basically just an offset sine wave, which multiplies the original waveform by 0 at the beginning and end of the window, and by 1 in the middle. Huh! Window functions destroy about half of the original data, where they multiply by 0 or very small numbers. For this reason, the Teensy audio library uses 50% overlap in its FFT1024 object. Yeah, so what we're getting, you're multiplying by 0 out here, and by 1 here, so you're sort of doubling the amplitude, the volume in the center here, and then going to 0 value for the wave on the edges. Huh. Twice as many 1024 point FFTs are computed, where the second set uses the window function offset by 512 points. I'm not sure why. Maybe if you're a little bit more experienced with math, you'll get this better. There's a surprising amount of math in audio electronics, but it's awesome. With the pure 220 Hz tone, this graph shows the actual Windows inputs to each 1024 point Fourier transform. A new 1024 point FFT is completed every 512 samples, because they are performed at twice the rate on 50% overlapping data after windows are applied. Okay, yeah, cool. So, you have this window, and then you do this window, and then this one, and that one, so that you always are repeating. Cool. So, because of the 50% overlap, FFT 1024.1 available will return true 86 times per second. Each new update of the data represents the prior 1024 samples, approximately 23.2 milliseconds, with a window applied, so it was most sensitive to the sound in the center of those 23.2 milliseconds, right there. Cool. Well, I think it's time to move on from spectral leakage and smearing, but there's lots more if you want to keep reading and playing around with this. Alright, finally, we're going to add the little graphical display, which is really exciting. Okay, so, in this last part, you'll connect a TFT display for the visualization of the peak detect analysis. So we did the peak detection before, and that was that cool little back and forth wavy thing. Step number 1, add the TFT display and connect the 5 signals. So first we have to disconnect the Teensy, because we don't want to cause problems. I'm also going to pull it out from the audio. Take a sip of tea. I might need a scissors. Why did I come to this workshop without my tools? I'm going to do this in kind of a BS way and use one of my little jumper wires to attempt to pierce this anti-static packaging. We'll see if it works. Oh yeah! We can do it. Okay. It's better to use actual tools, of course. But this is why it's called hacking. I'm sorry for abusing your kit, Paul. Please forgive me. Okay, cool. So we're gonna plug this into the breadboard. Where? To the right of the little... Okay. So, when you get this, you can see that there's some extra little silver wires on here that haven't been connected yet. Fantastic, and I just plugged the board in there, the display. So let's see. I'm gonna pull it off its little foam thingy. And where these two silver ones overlap is where the leftmost pin goes. Choom. Awesome. And now I'm going to plug in my jumper wires, which I have now scattered all over. Great. Let's start with purple. And these go, let's see, in the third pin. I'm missing one somewhere. Here we go. Then two over from there. That's my poor abused green wire. And then we've got 3 in a row. And then this one goes on the end. And now where are we plugging these in? Your breadboard already has the 3 volts and 1 ground connections installed, and that's going to be these guys, presumably. 5 colored wires are needed to complete the data path. So where are we putting these? Purple goes to Teensy pin 21. Breadboard row 58A? They give us breadboard rows? That's way too cool. So that's over here. I've never even used breadboard coordinates before. That's cool. 5, 6, 7, 8. Then we've got green going into Teensy pin 20, which is breadboard 57A. Kind of feels like I'm playing chess. As you can see on the breadboard, you've got letters along here, and then numbers going this way, increasing, ascending. We've got brown in Teensy pin 7. Oh yeah, and when it comes to pin numbers, you can just about read them. Oh no, you can't. I thought you could read them from the side. Okay, so pin 7 is 55J, which is over here. That's brown. And I'm poking myself in the face with electronics, which is fun, but not usually a good part of my workday. 51A is where orange goes. Things are getting a little crowded here. And then gray goes into 50-J over here. Cool. It also gives me the numbers for where these go on the display side. Let's just double check. Purple is in 7J. Cool. Green is in 5, 4, 3, and then 1. Cool. So now we're going to design our audio system for this. Let's just give you a closer look of that. I hope you can see this. We're gonna go into our GUI, grab a play SD wave piece, objects, an I2S output, and a couple of peak analyzers like before. I remember this. I did this kind of a thing with it. I prefer the like squid configuration. This has got a little overlap, which kind of makes sense, grouping similar objects together. Now we're going to export this, grab it, and throw it into the 3-3 example. Super exciting. Final example, guys! It's been so many weeks. I'm getting so old. There we go. And reconnect it, verify the sketch, and upload it to Teensy. Oh yeah! Try not to destroy your entire... Ooh, look, the thingy came on. Also, it's got this sticker on it that tells me that the factory approved it, I think. I'm just gonna leave it on for now, because I have a tendency to break things. I'm sure you can empathize. Yeah, so let's upload this. Come on. See, the thing is, the hard truth is that it stops playing the music while the compiling is happening, which is when I really feel like I should be sitting here and jamming out. But, oh well. Hopefully this rapidly updated TFT example may inspire you to continue exploring with the Teensy audio library. Well, I'm really excited to see it. So instead of looking at the serial monitor, this time we're going to see the numbers go up and down on here. Exciting. And thank you for bearing with me during this Twitch experiment. Hopefully we're going to have more awesome video stuff for you in the future. And it's going to work better, and it's going to look better, and it's going to be better. We're going to get a better looking host. It's going to be excellent. Done uploading. Why aren't we making the things happen? Ah! Let's have a look. Do I have to push anything? Maybe I did it wrong. Something is off. At least I got this soothing music to keep me from freaking out. All the other wires look like they're in the right place. And 7, yeah. $55J, $50J, 51A. Oh, 51A! Aha! That'll do it. You know, pretty much every workshop that we do, there's one wire that is just not connected right. And everything goes crazy. Wait, 51A? Yeah, 51A, 57A, and 58A. Those look good. Let's try resetting. I'm pretty sure that's the reset button. But we're not getting music now. Oh, yes! Oh my god, check it out! Thank you for joining me on this epic journey of Teensy audio in 4 parts, concluding with this fabulous peak meter on the little video screen backlight. It's very exciting. I've had such a good time with you over the last few weeks. I feel like we've really grown and got to know each other so well. I want you to sit back, relax, and just enjoy the rest of your Thursday. From all of us here at Hackster, thank you. And we hope to see you again very soon.